So in this video we're going to introduce subdivision of chains and simplices. Okay, so so for example, here's a space X, and here's a path. So here we can regard U as being an element of S1X, the singular one simplices in X, and those are the. And then you've got your group C1X of chains, which are linear combinations of such simplices. And for various purposes, it's going to be convenient if we can divide this thing into two. Okay, so obvious sort of thing we can do. Well, we just divide it into two parts, like this part and this part. And you might think that the natural thing to do would be to put arrows kind of pointing forwards. But it turns out that bookkeeping works better if we kind of think of the subdivision as the second half minus the first half backwards, as it were. Okay, so so if we call this one U0 going forwards, the second half of the thing going forwards, and U1 here as this first half going backwards, then we're going to define the subdivision of U is U0 minus U1. Okay. So I have a plus U0 because U0 is running in the same direction as U, and a minus U1 because it's running backwards. Okay, so we've now cut it into two halves that are smaller, and it's going to be useful later if we can just represent any homology class by a linear combination of very small simplices. That will turn out to be useful for building the Maya-Vittori sequence. Okay, so so that's what we mean by the subdivision of a one chain, and we do the kind of obvious sort of linear thing. If we you extend this linearly, so if we've got some finite linear combination, M1U1. We just do M1 times the subdivision of U1 up to MR times the subdivision of U1. Okay. So that's how we divide a one chain. We need to discuss how to divide up sort of n chains where n is bigger. But before we do that, let's just kind of discuss a slightly different way to express this definition. Okay, so and the kind of key point here is we just here's our simplex delta 1. And what we're doing is we're just subdividing delta 1 and then just applying U to that subdivision in a certain sense. And so a good way to think about this is as follows. So the endpoints of delta 1 are called E0 and E1, and then the point in the middle are called E0, 1. Okay, and so let's put theta 1 is the chain where we go from E0, 1 to E1, the linear chain like that. So it's just the obvious kind of linear map from delta 1 to itself, which fills in the right-hand half, and then minus E0, 1, E0. Okay, so that's so this we can think of as being a one chain in the simplex. So that's an element of C1 delta 1. And then what's this? Our subdivision of U is well, it's we said it's U0 minus U1, but what is this U0? U0 is kind of the right-hand half. U0 is the composite. Okay, we take our delta 1 and then we do this path E0, 1 to E1. That goes us to delta 1, and then we do the original U, which was a map to X, and that's what our U0 is, right? This is the thing that sort of sends delta 1 to the right-hand half of delta 1, and then we apply U. That gives us this U0 here. Whereas U1, that's what we get by doing delta 1, and then we do this linear path E0, 1, E1, E0, going to delta 1. That's the thing that fills in this left-hand half, going backwards of the one simplex, and then we apply U here, go to X, and that's what our U1 is. Okay. So another way to say this, right, is we've got our u. This gives us a map, a u lower hash, from the 1 chains on delta 1 to the 1 chains on x. Okay? And whenever you've got a continuous map, you've got a corresponding map of the chain groups. So we can think of this as being u lower hash of this theta 1. So to do u lower hash of theta 1, the way that was defined, we take u and we compose it with this first thing, and minus u composed with the second thing. U composed the first thing, as we said here, is just this u naught, and u composed the second thing is this u1. So the subdivision of u is u hash of theta 1. Okay, and so yeah, in order to sort of set up the definition of subdivision, we just need to provide this theta 1 and then apply u hash to it. And that's going to be a convenient way to extend this definition to define subdivision of higher dimensional chains. Okay, so now let's think about subdivision of two-dimensional simplices. Okay, so here's our two simplex. With 3 vertices, E0, E1, and E2. And I'm going to divide each of the boundaries, each of the edges. So this I'm going to call E01 here, E12 here, and E02 here. And now I'm going to mark in. So effectively what I've done here is I've taken, we know we've discussed already how to divide a 1 simplex. Each face of the 2 simplexes are 1 simplex, and we divided those up according to the pattern that we already established for 1 simplices. Then what we're going to do is we're going to sort of connect everything up to the middle. This central point here I'm going to call E012, and we're going to connect everything up to that. So now we've divided the 2 simplex into 6 2 simplices, and we want to take some of these with appropriate size. Okay. So we're going to define theta 2 as a kind of subdivision of the 2 simplex. I won't bother spelling out the sign plus or minus signs for the time being, but it's going to be like this. We take each of the well, actually, let's say we're going to do theta 2 prime first. So that's going to be the kind of subdivided boundary with appropriate plus or minus signs. So this we've got firstly, we've got the subdivision of this edge here, which is going to be okay. So we get just 2 pieces of this bottom bit, and then we do the same thing, say, to this edge here. So you get E12, and the same for this edge here. So you get E02, E0. So we get these 6 subdivided boundary pieces, and then theta 2 we're going to join everything to E012. To get so we get 6 terms here, and you end up with like E012, E02, E2, corresponding to this bit here. Okay, so that's what's going to be our theta 2. Okay, and of course, yeah, this thing here, and this is a linear combination of two simplices in delta 2, so this is an element of C2 delta 2. Whereas this one here, this is an element of C1 delta 2. Okay. Okay, and then if we've got a continuous map U from delta 2 to X, then we can apply that to any 2-chain in delta 2 to get a 2-chain in X. And so we apply that to all these 6 pieces here. We get kind of 6. You've got your U your original U is kind of giving you a triangle, maybe a curved triangle in X, and then applying U hash to each piece here gives you a kind of smaller curved triangle in X, and you add them all up with appropriate signs. That's what you get. That's your U hash of theta 2, which is the subdivided thing. Okay. So that's how we do our theta 2. And then for theta 3, we're going to do the same sort of thing. You've got a tetrahedron, and here's our delta 3. Okay, and so now we know how to subdivide a 2-simplex. So we divide. You've got 4 faces here. You divide each of those according to this sort of pattern, and then you join everything up to the middle of the tetrahedron. Okay, so that's how we're going to do theta 3. I'll have kind of more formal definitions in a minute. But let me just kind of say a little bit more about where these terms are coming from, sort of in a formal sense. Okay. Yeah. So this let's look at this this group of terms here, corresponding to this edge of the triangle here, right? So what's this edge here? Remember we've got these maps delta I from the 1-simplex to the 2-simplex. Okay, and this one here, this is delta 0 of delta 1. Is that edge there? The edge here is delta 2 of delta 1. This edge here is delta 1 of delta 1. Okay, and this this guy here, this gives me a map from chains on delta 1 to chains on delta 2. So how should we think about this group of terms here? Okay, what have we done? We've taken our normal. You take your normal theta 1, which is the subdivided 1-simplex, and then we've pushed it. We've pushed it into the 2-simplex onto this edge here. So what we've done is we've applied delta 0 to it. That's what these terms here are. This is what we get by taking our theta 1 and pushing it forward using delta 0 to get a chain on this edge. And similarly, this group of terms here, this is delta 1 hash of theta 1, and this one was delta 2 hash. Okay, so this is how we got our theta 2 prime. We take our theta 1 and we push it forward onto each of the edges of delta 2. And then we do this business of connecting everything to E0, 1, 2. So that's kind of a sketch of how we're going to define all these theta ends, and we'll do the more formal version in the next video.